All right, so welcome everyone to this HEP-TN seminar. Today we're very happy to have Laurens Lootens from Frank Verstraete's group at Ghent. And today he'll be telling us about some interesting and exciting properties of PEPS representations of topologically ordered states. So Laurens, thanks a lot for giving the seminar. Please, the floor is yours.
Yeah, thank you very much, Suki, and the other organizers for inviting me and for organizing this very interesting series of lectures. There have been so many great talks already, and I'm very happy to be a part of it. So as you said, today I will be talking a bit about PEPS representations of topologically ordered states, also critical lattice models, but mainly about MPO symmetries, so matrix product operator symmetries, and matrix product operator intertwiners. Now this talk is based on recent work that we did, well, together, so me, Ito and Frank did together with Jürgen Fuchs and Christoph Swigert, which has been put on the arXiv. And I will be also using some results, some older results that Robijn van Hoven, Matthias Bal, Dominic Williamson, Nick Bultink, and also Ito and Frank obtained. This is the paper on the strange correlator, which is about the mapping between topologically ordered states and critical models, and then also some more recent results in this paper. So the outline for this talk is, first I will give a very quick overview of symmetries in tensor networks, talk about why they are important, how they work in MPS, how they work in PEPS. This will naturally lead to the concept of MPO symmetry algebras, and we'll explain what these are, what the consistency equations are for these things. Then we will take a bit of a mathematical detour. I've tried to keep it as simple as possible, but I have to talk about it. It's bimodule categories, and I will introduce them in the context of string net models, which is the most physical way you can look at it, and it's really not that hard if you do it that way. This will allow me to construct explicit MPO symmetries and then also the MPO intertwiners. We can use these for a variety of things. Amongst these are actually construct domain walls between different topological phases. Now, you can also show that these PEPS constructions and their MPO symmetries, they have a very natural interpretation in terms of Turā-Viru topological field theory. So for people who are more familiar with these concepts, this provides a very nice link to that. And then hopefully, if there is time left, I will talk a bit about critical lattice models and explain how we can understand things like orbifolding directly on the lattice. So let me start by talking about symmetries in MPS. So I hope everyone knows what an MPS is. This is my depiction of an MPS. It's translationally invariant, n-sides, periodic boundary conditions. Now the most important theorem when you're talking about symmetries in MPS is the fundamental theorem of MPS. Now this theorem states that if you have two MPS that are generated by a different tensor, so you have some tensor A and a tensor B, but if they generate the same state for any system size, then there should exist a gauge transformation X that basically intertwines between these two MPS tensors. Now, you can immediately apply this to the case where this MPS has some global symmetry, some UG, acting on this psi A. If this state is symmetric under this action, then this implies that this tensor A acting on it with UG has to be related to this A by again such an intertwiner. And this intertwiner, well, this X, this gauge transformation, depends on the specific group element G that you are taking. Now, for consistency, if I do this twice, so if I act with a UG and then a UH, if I want this to be consistent, I should have that this X forms a representation of my group. Now, if you were to bring this X to the other side, you would get an inverse here. And you would see that it's actually enough that this is a projective representation. This doesn't have to be a linear, well, this doesn't have to be just a normal representation. It can be a projective representation, meaning that there can be a phase here. Now this phase, this would drop out precisely because I'm taking the inverse here. And this phase depends on the specific group elements G and H. Now you can write down a consistency equation for this omega of G and H, which is called the two co-cycle condition. You basically get it by saying that the product of three of these guys should be associative. This gives you a consistency equation. And this basically provides you it gives you the SPT classification in 1D, because this two co-cycle here is characterized by the second cohomology of this group. And basically what it means is that if you have an MPS that transforms projectively under this group representation UG, and you take another one that transforms under a different projective representation, you cannot connect these two without breaking the symmetry and while keeping injectivity of your MPS. So there's really different classes of MPS, and this is, well, these are precisely these symmetry protected topological phases. Now, you want to do the same thing in 2D, and in 2D you have to talk about PEPS. And so you want to consider something like a fundamental theorem of PEPS. Now, this doesn't exist in full generality. There have been, well, special cases of PEPS. It has been proven that such a theorem also exists, but it doesn't exist in general. Nevertheless, you cannot write something like this. So if you have a PEPS UG acting on this psi A, and it's again, so this state is symmetric under this UG. If you write this down at the level of the local tensors, you get an equation like this. So you get that this UG acting on your local tensor A, so this is A, should be an A here. So this should be A, this is also A. You basically get the same thing as in 1D, but now in 2D, and you have basically these gauge transformations acting on these two legs, and they basically intertwine this PEPS with this PEPS tensor. Now, this is not the most general case, and in fact, you can allow the virtual action of this group on your entanglement degrees of freedom of your PEPS to be represented by a matrix product operator. So this is represented by adding these additional lines here. So in this top picture here, these are just tensor products. So these x's are acting as a tensor product on these different legs of the PEPS. Here, this is no longer the case. So this is really now a matrix product operator. There is some contraction going on here. There is some entanglement between this operator and this operator. And if you allow for this, you actually get the same thing as in 1D. You get the SPT classification in 2D in terms of the third cohomology. I will come back to this a bit later. Now, if you just want to consider intrinsic topological order, so for the case of SPT, there is some global symmetry under which your state is invariant. But in 2D, you already have intrinsic topological order. So this is just a case when you have such a purely virtual symmetry that you can pull through the lattice without there being an action on the physical level. Now, if you purely restrict yourself to virtual symmetries, there is no reason to restrict yourself to invertible MPOs. This doesn't have to correspond to some unitary operator on the physical level anyway. So we can do something more general on this, and we can actually consider MPO algebras. So MPO algebras, well, we want to kind of try to characterize, well, so this is the whole point of this talk, trying to find out what properties does the PEPS have to satisfy, what properties do these MPOs have to satisfy in order for them to be a purely virtual symmetry of such a PEPS tensor. So to characterize this, you start with the simplest instance of a PEPS. It's a PEPS with 3 legs. Now I'm using a bit of a simplified notation here. I should really be drawing extra boxes like this here and an extra box like this. So anytime there's a crossing of red lines with a black line, or where black lines come together, there is actually such a tensor. So I will be using this simplified notation. Now, first thing you want that this MPO is actually symmetry. So this is expressed in this equation, this pulling through equation we call it. Now, you also want there to be, well, if you have one such MPO symmetry and you have another one, if you multiply them, it will just again be an MPO symmetry. Now, either you have an infinite amount of MPO symmetries, in this case, you cannot deal with them, or you have a finite set of them. And in order for them to be, well, in order to have a finite set, you need these different MPOs to be closed on the multiplication. Now there's a label in these MPOs here. This label, it's label A and this label B. This label A and this label B are labeling the injective MPOs. So in general, your MPO will look something like this. You have some I, some J, and this will be a matrix, and it will look something like this. Now, in general, these MPOs can be decomposed. They can be brought into a canonical form where they have the following block diagonal structure. And then this A label here is really just labeling the different blocks in this decomposition. It should be noted that in general, you can have these off-diagonal blocks in your canonical form of your MPO. On periodic boundary conditions, these will never contribute. So if you only consider MPOs on periodic boundary conditions, these blocks do not play a role. However, they will play a role if you look at the local relations. So for that reason, we will assume these off-diagonal blocks to be zero. So okay, you require that this thing is closed on the multiplication, and that there is some finite algebra, which means, well, if I take one of these MPOs, so this is an MPO that you put on periodic boundary conditions. This is another one that you put on periodic boundary conditions. You multiply the two, and you get again a sum of injective MPOs with a fusion coefficient, this NABC here. These are just integer numbers that tell you if you multiply these MPOs, how many times does this block appear in the composition, in the decomposition of these two guys. And so this is required if you want a finite set of these MPO symmetries.
Laurens, can I just ask a quick, slightly technical question?
Yes.
So these individual MPOs, you're assuming they're injective.
Yes.
Worse, I mean, so they are not normal, like they're actually injective, meaning this individual tensor can be inverted. Like you can find some tensor that you contract with this so that you can eliminate this tensor.
Yeah, indeed.
Is that right?
Yes, it is injective when viewed as a map from these virtual indices to the physical indices. So there exists a map, something you can put on these physical indices to basically remove this MPO tensor. That's indeed what it means. It's just the same thing as for MPS. So you have an injective MPS, injective MPOs are precisely the same.
Right. But my emphasis was, so it's actually injective. It's not injective after blocking.
Oh, right. Yeah. It's already injective indeed before blocking. Yeah, you're right. Yes.
Thank you.
This will come up again later. So indeed, it's a good remark, and I will mention this again. Right. So if you have this equation here, you can actually look at this as MPS by basically bending down these legs. And these are just two MPS. And these are two MPS that are the same for any system size. And this means, again, if you use your fundamental theorem, that there exists an intertwiner, such an X, that you can basically use to intertwine these two MPS and translate it to the case at hand. This just looks like this. This looks like this. So this is just this X that we had before. Now, this is what we call a fusion tensor. This fusion tensor is labeled by, well, you have one fusion tensor for each combination of A, B, and C. Now, I've said that there are multiple ways. So this NABC basically labels the ways in which an MPO of type A and an MPO of type B can fuse to an MPO of type C. And so for each one of these possible fusion paths, there exists such a fusion tensor, and this M is labeling which one of these you are taking. Now, the fusion of the multiplication of 3 of these MPOs, well, it's just matrix multiplication, right? So this should be associative because matrix multiplication is associative. And if you translate this to a condition on these fusion tensors, you arrive at the following condition here. You see that if I first reduce A and B, and then reduce the product, well, if I then reduce E and C to D, or if I first take B and C and then multiply this with A, these two fusion tensors, well, these two tensors should be related by some unitary transformation. And this unitary transformation is given by this thing here that we denote as 0, F, A, B, C, D. So it's a map from the space, well, it's a map from E, J, and K to F, M, and N. Now, it's important that this F doesn't depend on the precise details of this fusion tensor. It only depends on which specific injective MPO label you are using here, but it doesn't depend on the details of this tensor here, which is an important thing. Now, we've considered the associativity of 3 of these guys. You can also consider, well, you can also express that the multiplication of 4 of these MPOs has to be associative. And if you do this, there's basically 2 equivalent ways in which you can go from, well, this part over here where you first take A and B, then C, then D, or this part where you first take C and D, then add B, then add A. There's 2 equivalent ways of doing this. And this equation, this basically imposes some consistency equation on these F symbols. And this consistency equation is the pentagon equation. So that's, oh, it looks like this. There's 2 F symbols, well, 2 0 F symbols on the left-hand side here. And there's 3 F symbols on the right-hand side. Now, we should note that for MPOs that fuse according to a group-like structure, so where you don't really have an algebra, but a group, this pentagon equation reduces to the 3 co-cycle condition. And it's precisely this equation that has solutions that are classified by the third cohomology. And so this is what gives you all the SPT phases in 2D. Now, moving on, your pulling through equation, because of the fact that this has to hold for, okay, the precise reason that this vertical fusion tensor should exist is a bit technical, but basically it comes from the fact that this pulling through equation should hold for any value of the physical indices. Now, what are these black labels now? Well, I've said that we are assuming that, so the MPO IJ like this has some block diagonal form. You can also consider a block diagonal form in the vertical direction. So what you do then is, instead of looking at it as a matrix from left to right, you look at it as a matrix from the bottom to the top. And then this is also matrix, and then you can also just block diagonalize this. And so what this alpha, beta, gamma are labeling are just, again, these different blocks in the vertical direction now. So you get such a vertical fusion tensor. Now this vertical fusion tensor, this has to, again, be associative, which you can express, again, in the same way. There should be some unitary transformation that transforms between the left-hand side and the right-hand side here. And we call this, well, a 4F. It's a different symbol than before. And this 4F should, again, satisfy a pentagon equation. Now, it's important to note that the 0F symbol that we derived for fusion in the horizontal direction and the 4F that we derived for fusion in the vertical direction can, in general, be different. That's actually one of the key insights of this paper, is that they indeed can be different, and that this leads to interesting things. Now, I should. Sorry, is there a question?
Oh, I thought you answered my question with your next picture, actually. Okay, so here, this triple black line tensor with the K is the PEPS tensor with some physical index fixed to value K. Yeah.
Yes, indeed. So the point here is that you can take your PEPS tensor to be equal to this vertical fusion tensor, and then your PEPS tensor will actually satisfy this equation. This equation is nothing but the Levin-Wen condition in this, guys. So if you bend one of these legs down, you see actually that this is the Levin-Wen condition. So if you take your PEPS to be equal to this vertical fusion tensor, that means that you are at an RG fixed point. But it's important to state that this MPO symmetry business, it also works if you're away from the RG fixed point. So in general, a general PEPS will be some symmetry layer that is determined by this vertical fusion tensor. And then there will be some variational degrees of freedom that you get add onto this, just like the way you would do for something like SU2 symmetric tensor networks. You have some layer that encodes the symmetries, which would be the Clebsch coordinates in that case. And then there's some variational degrees of freedom. Here we are just saying, well, these variational degrees of freedom, they are not there. And that means that you are at the RG fixed point, but in general, they can be there.
But then, sorry, but then are you saying that this pull-through equation that you have on the left-hand side with the red line pulling through this K tensor, this is not the pull-through we had at the beginning with the PEPS tensor? Like, I mean, so there is one choice of PEPS tensor where this pull-through condition reduces to the condition you had.
Yes.
But in general, this is some fusion tensor, different from what's there in your PEPS tensor.
Right,
this
indeed.
vertical fusion tensor. But then how do you, what is this, where do you get this pull-through condition from then? Is it seems to be related to the first condition you mentioned with this red line being able to cross through the PEPS tensor, but is it that, what's the relation with the, yes?
You're asking where this is coming from?
Yes.
Well, it's basically if you, so go all the way back to this equation here,
right.
You can consider this. So you have some MPO and you bring it into this block diagonal form along the vertical direction now. So not in the horizontal direction, but in the vertical direction. And if you do this, then this equation should hold basically for any of these blocks. And that's basically where this equation is coming from. I'm skipping a bit over the details. It's actually a bit of a technical argument. Okay. Also has to do with the fact that this MPO symmetry is an RG fixed point itself. So this vertical fusion tensor, you can interpret this as something that actually coarse grains your MPO. And the fact that your MPO itself is an RG fixed point is what leads to this existence of this vertical fusion tensor. But it's a bit technical and I really don't want to get into it too much.
Yeah, no, sure. Yeah, thanks.
But indeed, it's an important point. So in general, so the general pulling through equation is when you have this tensor, you can have an additional layer living on top here that basically encodes some variational degrees of freedom. But I think I'm making it more confusing than it should be now. So let's for now just assume, and that's also the only case I will be talking about in this talk. Any case, that this PEPS tensor is really equal to this vertical fusion tensor. In the end, we find these 6 coupled consistency equations for the presence of an MPO symmetry in a PEPS tensor. So 2 of these are just the pentagon equations, well, 2 pentagon equations. So you have a pentagon equation for 0f, and you have a pentagon equation for 4f. Then, well, you actually know a tiny bit more than this. So you actually know that this isomorphism here is a 0f and this isomorphism here is a 4f. But other than that, well, these are the coupled consistency equations that you have to solve if you want to find an MPO symmetry in a PEPS. So it's the pentagon equation for 0f, it's the recoupling of your fusion tensor, it's the zipper condition, it's the pulling through condition, it's the associativity of this vertical fusion, and then pentagon equation of this vertical fusion. So this is the objective here, is to find solutions and classify the solutions to these equations. Now for this, we'll have to make a bit of a detour. And it turns out that you can explain these solutions in terms of bimodule categories. Now, I assume that most people here are not familiar with what this is. But this is actually a very nice mathematical construction. You can see it as like a generalization of representation theory, but for categories. But fortunately, it pops up in a very natural way if you are looking at string net models with boundaries. So to recall what actually a string net model is. So string net model is a construction by Levin and Null when it provides you a microscopic realization of an RG fixed point. It's completely determined by specifying some fusion category C. So what is this fusion category C? It's something that has simple objects, A, B, and C. There is a functor that takes a pair of these objects and maps it to a new object. It's basically something like a tensor product. And this functor, well, there is an isomorphism, this 0f, between first taking A and B and then C, or A, B and C and then A. So it's basically, this functor is associative up to some isomorphism. And then the ground states of this Levin-Wen model basically have to satisfy this equation, which basically states that if you look at this from far away, it doesn't matter how you resolve this vertex, which means that you are at an RG fixed point. But this is only one of the Levin-Wen conditions, but this is the most important one. And so it's completely encoded by this 0f here. And then the Hamiltonian of the Levin-Wen model is really just, you have something, well, you have this vertex term here, which basically just enforces the fusion rules at such at a vertex. And then you have the plaquette term, which basically ensures that your ground state is the superposition over all allowed configuration. Now, if you want to consider a Levin-Wen model with a boundary, you need actually something more than just a fusion category. And this was figured out by Kitaev and Co. So a boundary of a string net model is determined by a C module category M. So what is this thing? Well, we have some string net model here in the bulk. And we want to know what are the possible boundary conditions for this string net model. So this thing here will be a boundary. What do I need for this boundary? Well, okay, there are again some simple objects in this boundary. And there is a functor, it's called the left action, that takes a C, an object from C and an object from this module category, and maps it again to some object of the module category. So this is because we have some, well, if you have some degree of freedom living here, that's labeled by M. You have something labeled here, that's labeled by C. You want it again to go to something in M. And that's the reason why you write down something like this. Again, there's an isomorphism for this, this functor, which basically states that it doesn't matter if I first fuse two things in the bulk and then with the boundary, or if I fuse them one by one with the boundary. These two things are isomorphic up to some isomorphism 1f. Now, if M is also a D module category, then it's just the boundary of some string net model D, a different string net model. So this again, well, it requires some simple objects, alpha, beta, gamma in D. There's some functors, M times D going to M, and then just the normal, well, D is just a fusion category, so there's the normal tensor product of the fusion category. And then there's two additional isomorphisms. So in this case, M is actually a, it's a right boundary of the string net. So on the right-hand side here, you have string net living in the bulk, and then this is some boundary to the string net model. And then this here is just the usual recoupling equation of your bulk on the right-hand side. Now, if you want to consider a domain wall between two different string net models, so string net model C and D, you need that, well, you need a category M, which is both a boundary for the model C and a boundary for the model D. Now, additionally, if these two boundaries are compatible which is just saying that it doesn't matter if I first fuse with something from the string model on the left and then on the right, or with something on the right and then on the left. These two things are isomorphic. Then this thing is called a CD bimodule category. So this is really all there is to these bimodule categories. It's just a bunch of objects, a bunch of functors, and then some isomorphisms that express the associativity of these functors. Now, so in the end, we have 5 different F symbols that if you calculate, well, if you compute the consistency equations that they have to satisfy, you find these 6 coupled pentagon equations. So 2 of these we already encountered. So these are just the normal fusion category pentagon equations. You have this for the 0F here, and you have this one for the 4F here. And then these are new ones. So these basically express the fact that all these functors, all these isomorphisms have to be compatible with each other. Now these are actually quite complicated equations, but I'm just presenting them in a very simplified way here. Now, the key observation of this new paper is actually that these bimodule pentagon equations, they coincide with these MPO symmetry consistency conditions. So you had these 6 equations here, you have these 6 consistency conditions here, and we actually make the following identification as such. So, well, these 2 we already had, and then we are just identifying these 4. So the associativity, zipper condition, pulling through condition, and again the associativity with these bimodule pentagon equations. The way you can do this is by making the following explicit assignments. So you say that this fusion tensor is really a 1F symbol. The MPO symmetry, the MPO tensor is a 2F symbol, and the PEPS tensor is a 3F symbol of some CD bimodule category. So in this case, C is labeling the MPO symmetry algebra, and D is labeling the string nets that you are talking about. Now, if you've never seen this kind of notation before, it might look a little strange. You should really just think of this as you have these 3 lines here, and then this multiplicity label J. The way you interpret this as just a normal tensor network is you just group these 3 initials together into one fat index here. And then in the simplified notation here, we are just keeping the label A. So this label A is not running over all the possible inches of this tensor, it's just labeling this injective block here. Same goes for the MPO symmetry and the PEPS tensor. Now, one remark for this PEPS tensor, you could ask, well, where is the physical leg? The physical leg is actually just, for simplicity, we omit this, but this might be important to state this again. The physical leg is just, you have some physical leg sticking out here that's labeled by alpha, beta, gamma, and then this K. So the PEPS is something like this, and the physical degrees of freedom are really these middle indices here and this multiplicity K. So in the end, your PEPS representation of some string at model D is determined by a choice of module category M over D. Now it's important to note that you can always take M to be equal to D. You can consider D as a module category over itself. And then this actually reduces to the representation of string nets, the well-known tensor network representation that Boer-Schaper and co-authors derived many years ago. You can do something more general. You can allow this M to be something different. And then your MPO symmetry algebra, which is labeled, well, which is described by some fusion category C, is determined by the CD bimodule category M. Well, basically the objects, the data of this bimodule category, namely the MPO symmetry is a 2F symbol, and the fusion tensor is this 1F symbol. Now, this might have been a bit confusing, so let's just go to some examples because it's always easiest to explain. For example, Tori code, we take D to be the string net. Well, we take D equal to M equal to C. So we take all these categories to be equal, and we take them to be the category of Z2 graded vector spaces. This is just a complicated way of saying this is a category with 2 objects that fuse according to Z2 fusion rules. And if you do this, you recover this this well-known triple line notation, this triple line tensor network representation of the toric code and its fusion tensors. Well, I say well-known, this is actually not the simplest toric code representation. The simplest toric code representation is actually the following one. So this is where you take D to be just the category of Z2 graded vector spaces, and you take M to be the category of vector spaces. So this is it's kind of a trivial category. It only has one object, so there's not really much going on there. And all these different functors, they are kind of trivial. In the end, what it amounts to is you have just some PEPS tensor that basically implements your group multiplication. So G1, G2 goes to G1, G2. These triple lines here, they are not present in this case because M only has a single simple object, so this is always fixed. The MPO symmetries in this case are just sigma Z operators acting on these legs here, so that's what you can see here. And then the fusion tensors, again, just implement the Z2 multiplication rules. And so this bottom representation is actually the simplest toric code representation. That's the representation you would write down. And that has been written down first for the toric code PEPS. A bit more of a complicated example is where you take D to be, instead of just the Z2 graded vector space, you take it to be an S3 graded vector space where S3 is a symmetric group. This is the smallest example of a non-abelian group. So if you want to get something non-trivial, this is the smallest thing you can do. So again, the PEPS tensor is just something that implements the group multiplication. Your MPOs here are actually EREPs of this group, because the MPOs themselves turn out to be labeled by the representations of SD. Now, SD is not an abelian group, so these representations are not one-dimensional, and that's why you actually get these multiplicities here. And then your fusion tensor are just the Clebsch-Gordon coefficients of rep S3. Another example is where you just flip this entire thing. So you take D to be rep S3 now. This is really a string net model then. You again take M to be category of vector spaces and C to be vec S3. So you just flipped this case here. In this case, your PEPS tensor is a Clebsch-Gordon, your MPO is again an EREP, but now it's rotated 90 degrees, and your fusion tensor just implements the group multiplication. And this is actually the representation that people have been using when they construct G-injective PEPS. So these explicit MPO symmetries, they allow you a unified treatment of quantum doubles. So these are the models I discussed. Adjusted quantum doubles I did not discuss, but they fall completely within this representation, and string models. They also allow for a description of the ground state, so you can construct something that's known as a tube algebra. I don't want to go into this, seeing that I've already been going for 40 minutes. So let me just skip this maybe. Now, okay, I want to get to this point, MPO intertwiners. So I've said that if you take, so different choices of this module category M give you different PEPS representations of the same string net model D. Now you have two PEPS that represent the string, well, the same model. And much like a fundamental theorem for MPS, you want to say that, well, there's some fundamental theorem for PEPS, and then you can relate these using what we call an MPO intertwiner.
Laurens?
Yes.
Sorry, could you just remind me the category M, which tensors are determined by the data in this category?
Right, sorry. So let me just go back to this here. So you have this string model D. Your PEPS representation is completely determined by a choice of module category M. So this 3F here is actually a property of this module category.
Okay, so the PEPS tensor. Okay.
Yes, indeed. Yeah, the PEPS tensor.
Okay.
So a choice of M determines PEPS representation of string model D. There can be different PEPS representation of the strings, same string model, and you can relate these using an MPO intertwiner. So in general, you have two PEPS representations of the same string net model, where you take some choice of a module category M2 and a module category M1. Now, it will turn out that for the case where you choose your module category to be just some M here, and then here you take the module category to be D itself, so you take D as a module category over itself, then you can actually construct explicit tensors that correspond to this MPO intertwiner. Now, this MPO intertwiner, MPOs should be able to end on this MPO intertwiner in both representations. Now, this comes with a variety of consistency conditions. You have that this MPO intertwiner should be movable through the lattice. This should not be physically observable. So the simplest way to encode this is that it doesn't matter where you put this MPO intertwiner. You have this point where an MPO symmetry labeled by red can meet an MPO intertwiner, and it shouldn't matter where this happens in the lattice. And this gives you basically these two equations. And then you have basically just, again, the fusion of MPOs with this MPO intertwiner. The fact that this should be associative gives you these three equations. Now, again, using the following identifications, you can relate all these consistency equations to various of these bimodule pantone equations, and you can find explicit solutions of these intertwiners. Now, something that's very important to state is that while these two PEPS, well, so if you have two different PEPS representation of the same string net model, they are not necessarily the same state. And you can very easily illustrate this as follows. So you take some state psi1, which is a PEPS representation dependent, where you take D as a module category over itself, and then some psi2 where you take M to be some module category. You can actually relate these two states by inserting a small bubble of this MPO intertwiner here. You can grow this bubble to cover your entire system. So I didn't mention this, but this is all on the torus. So you can grow this bubble to cover your entire torus, and then you can resolve this basically again into MPOs of this PEPS representation here. And you see that this one and this one, they cannot be the same states. So they are different ground states of the same string net model. The way you can actually understand this is using these two algebras, but it's easy to see that there is no local operation that can convert this state into this state. So they are distinct ground states of the same string net model. Again, an example, so we had these two representations of the toric code, the one where we use these three lines, and then the one that's just a naive toric code representation. You can relate these by the following intertwiner, and then the statement I just said about these not being the same two states is illustrated by the fact that this representation with no MPO symmetries is actually equal to this other representations with MPO symmetries, which implies that if this picture were not, did not have MPO symmetries, these would be two different states. Now, another thing you can do with these bimodule categories is you can construct explicit PEPS representations of domain walls between two different topological phases. So what's different now is that we are now considering two different string net models with two different topological orders. So this Z of D1 and Z of D2, these are, well, the Drinfeld doubles of these string net PEPS. So they basically, well, this is what describes your topological order. And these are different in this case. And now again, it turns out that in the most generic case, we cannot explicitly construct these tensors. But if you restrict to the case where you take on the left here, the representation where you take D as a module category over itself, and here you allow for a generic M, you get this, well, you have these consistency equations, which are the equations I showed previously when I was explaining these bimodule categories. If you, again, make the following identifications of these tensors, so these are all the various tensors. This is the left bulk, this is the boundary with, well, this is the boundary to the left, this is the boundary to the right, and then this is the right bulk. Then again, these consistency equations correspond to pentagon equations of your bimodule category. So again, to illustrate this with an example, if you take the toric code and you consider boundaries to the vacuum, so this is the case where this stringnet model on the right is just a trivial model, it's not there. Then you get actually two types of boundaries. So you can have a boundary that's labeled by the same category as your bulk toric code, or you can have a boundary that's labeled by the same category as your vacuum thing. And these two boundaries have been known for a long time. This is called a smooth boundary, and this is called a rough boundary because if you, well, you still have degrees of freedom living on the edge here. So if you were to draw the degrees of freedom, you would just get a, well, your toric code thing would look like this. So you have your bulk model here, and it would end in a smooth line. While for the rough boundary, you actually don't have degrees of freedom living on your boundary, which is why this is called a rough boundary. Now, so this is a very simple example. Of course, there's much more complicated things you can do. But what these tensor network representations allow you to do is to put these systems on a computer. So these stringnet boundaries, they have been studied for a long time. They have been understood in terms of well, the abstract setting of category theory for a long time now. But if you actually want to do simulations using these models, using these stringnets with boundaries, you need actually explicit representations of these tensors. Now, something that we can do with this, for example, is to simulate something like a toric code, but instead of putting it on a torus, put it on just a plane with some boundary conditions. Now, this is much simpler to realize experimentally too. So if you want to construct a toric code in the lab, you would much rather put it on something with boundary conditions than put it on something like a torus. And actually, because these two boundaries have different properties, so the smooth boundary actually condenses magnetic excitations of the toric code. This rough boundary condenses electric excitations of the toric code. So if you have a rough boundary here and a rough boundary here, you can still encode qubits in the following way. You have some magnetic excitation that is condensed here. It cannot condense on this rough boundary, and it has to go all the way to this other smooth boundary. And so there is no local operation that you can do that just removes this string. And this is the way you can work with toric codes without having to, well, it's not called toric code, it's called surface code. So this surface code allows you to encode qubits in a non-local way without having to resort to these complicated toroidal geometries. I will maybe skip this part. The essential part here is that there is a way of understanding these PEPS and these MPO constructions as instances of some specific Turai-Viro topological field theory. So basically, what you do is you, well, what a TFT does is it takes some cobordism and maps it to vector space. Now, the way you understand these PEPS constructions is you have a manifold with two boundaries. So you have this white boundary, which is called the gluing boundary. This is a boundary to which the TFT will assign a vector space. And then you have this green boundary here, which is a physical boundary. And this will just get mapped to a scalar by the TFT. Now it's known that physical boundaries in Turai-Viro TFT, they are labeled by a module category. And actually, if you perform the Turai-Viro construction, you precisely get the PEPS tensor. You can also consider Wilson lines living on the boundary, and then you precisely reconstruct this MPO tensor. But I don't want to go into this more. So for the final part of the talk, I want to talk a bit about critical lattice models. Now, it turns out that these MPO symmetric tensor networks, they not only describe topologically ordered states, they also are capable of describing critical lattice models. And the way you can go from one to the other is precisely by this strange correlator that I discussed. So the idea here is you take some state which has topological order, so it's some state with an MPO symmetry, and you project out the physical degrees of freedom. So you take the overlap of this PEPS here with topological order with some product state. Now the essential part here really is not that this is a product state, it's that you are taking the overlap between two things with a different topological order. So on the one hand, we have some topological order, and on the other hand, in this product state, we have a trivial topological order. Now, from the field theory point of view, you expect this to be something critical. There has to be some phase transition associated to going from this this topological phase to this trivial phase. But this overlap is actually, well, this overlap is now just a number, and it's actually the partition function. Well, you can interpret this as the partition function of some Stalmec model. Now, the claim is that because this network here, so this partition function will also still have these MPO symmetries, they survive this projection just fine. Because this partition function has these MPO symmetries, you expect that this model will again be critical. The reason is that if you look at the transfer matrix associated to this Stalmec model, this transfer matrix will have an MPO symmetry, and you can actually show that the fixed point of such a transfer matrix cannot be an injective MPS. So if it cannot be an injective MPS, that must mean that either you have symmetry breaking or you are critical. And so for the cases that we will consider, it turns out that we get a critical model. And the way to actually understand this more deeply is that these MPO symmetries are able to protect you against relevant perturbations. So I will illustrate this a bit with the simplest example you can take, just the Ising model. So if you start from the Ising string net, Ising string net is a model where you have three particles. You have a 1, sigma, and psi. The fusion rules of the string nets are as follows. So sigma times sigma is just 1 plus psi, and psi is just a Z2 label. You can obtain actually the critical Ising model. So if you take the following product state and you put this on this PEPS, you can actually obtain the Ising model. I will not go into, well, I don't want to explain in detail how exactly this is the Ising model, but basically you get these loops sigma here that are fixed, and then this 1 and psi, they are your spin up and spin down degrees of freedom of your Ising model. You can, well, this is actually not the Ising model. This is known as an RSOS model. RSOS models are models, integrable lattice models that you build based on Dynkin diagram. So the Dynkin diagram for the Ising model is as follows. Now there are two non-trivial MPO symmetries. In this model here, you have the Z2 symmetry, which is just generated by the MPO labeled by psi here, which is just the ordinary spin flip symmetry. And then you have this sigma MPO, which basically is a lattice implementation of the Kramers-Wanier duality. So if you have these two symmetries, you are basically forced to be at the critical point, because Kramers-Wanier duality basically, well, it flips low temperature to high temperature. And if you enforce that this is actually a symmetry, then you have to be at the critical point. And so when I was talking about MPO symmetries excluding relevant perturbations, this psi, this Z2 symmetry, this O psi MPO, basically it excludes perturbations in the form of just a single Z operator, so a magnetic, adding a magnetic field to this. And this O sigma here protects you from changing the temperature. And these are the only two relevant perturbations in the Ising model. So you are protected against these two by having these MPO symmetries. The CFT associated to this critical model is just the critical Ising model. It's a CS1/2 minimum model with the following diagonal partition function. And if you diagonalize this transfer matrix, you get the following spectrum. So you get these different conformal towers. And using these MPO symmetries, you can actually project onto different conformal towers. But this is not something I want to get into. Now, a generalization of this Ising model is a three-state POTS model. Instead of starting from the Ising category, you start from the Z3 Tambara Yamagami category. It's just a complicated name for adding one extra, well, in the Ising model, you had this, this Z2 kind of sub-algebra subgroup. Now you have a Z3 subgroup, and again, this sigma, which if you take the fusion product with itself, is just again able, is equal to A plus B plus C. You can again, you can obtain the three-state POTS model by starting from this string net. In terms of RSOS models, this is this Lincoln diagram. If you diagonalize this critical lattice model, you get a CS4/5 minimal model with a non-diagonal partition function. So the POTS partition function is actually non-diagonal. Non-diagonal because you have these characters here, and well, basically, if you actually write this out, you get these cross terms. So, for example, you get a chi0 and a chi3 bar, and all these other non-diagonal combinations. Now, the reason this is actually a non-diagonal partition function is because you can understand the three-state POTS model as an orbifold of the tetracritical Ising model. So, tetracritical Ising model is the same CFT, but it's with a diagonal partition function. So it's just another modular invariant that is diagonal, and that's of the following form. So this one is diagonal, it doesn't have any cross terms. Now, how can you understand this orbifolding relation between POTS and tetracritical Ising directly on the lattice? Well, it turns out that if you take a string net that's described by this SU2 level 4 category, and you write down a PEPS for this string net model, where you take D as a module category over itself, or you take this Z3 Tambara Yamagami module category as module category of D, and you write a different PEPS, then it turns out that this one here corresponds to the tetracritical Ising model, and this one corresponds to the three-state POTS model. Now, so these are the, well, this is the Dinkin diagram of the tetracritical Ising model. This is the Dinkin diagram of the three-state POTS model. You can, again, using a similar argument as before, using this MPO intertwiner, inserting a bubble into this representation, you can actually show that this three-state POTS model is equal to this tetracritical Ising model, but with the insertion of some MPO symmetries. And so this will give you a twisted partition function, which just gives rise to these non-diagonal characters in the POTS model. So this is a very nice way you can understand this this orbifolding directly on the lattice. So that's about all I wanted to say. As for an outlook, so the things you want to further do with this is I've mentioned it, but I didn't really go into it, is that you can use these MPO symmetries to construct different ground states using these tube algebras. You can also use these tube algebras to construct excitations. And then you look at what is the interplay of these excitations, these tube algebras with these intertwiners. You can actually extend the tube algebras, more general excitations. For example, if you take two string net models with a domain wall in between them, the excitations on the domain wall can be richer than the excitations in the bulk. And this is actually useful for something like topological quantum computation. You can get non-abelian onions out of an interface between just two abelian models. Another thing you want to do, you can do with this is simulating phase transitions, but this is related to these invertibility of bimodule categories, which I didn't really talk about. As I said, you want to be able, the fact that you have these explicit PEPS representations of string net models with domain walls allows you to simulate them, allows you to calculate things like error thresholds for quantum error correcting codes on such models. Another very interesting generalization of this would be to include the case of fermionic bimodule categories. And then finally, well, the big problem here is just solving these pentagon equations. So I mentioned that you get these 6 coupled equations for a bimodal category. In general, these are very hard to solve. You can solve them in specific instances, and for something like a group, these have been solved. But if you want to generalize this orbifolding thing to include, for example, the full ADE classification of the minimal moles, you actually have to solve these pentagon equations. And we are making some progress on this. This is a hard problem. And then, well, there are many other things that we expect that we can do with this, but that's about all I wanted to say. So thanks.
Yeah, thanks, Laurens. Maybe we can all unmute and thank Laurens. Okay, questions? Maybe I can ask one there. Laurens, are you there?
Yes, yes.
Yeah. And then this strange correlator construction, right? So is there a systematic way of, so you're building a critical lattice model from a topologically ordered PEPS, right?
Yes.
So suppose I want my favorite rational CFT or whatever to come out this way, right? So is there a systematic way to understand what PEPS I should start with and what projection I should do? Or is it limited to, like, you have to do this on a case-by-case basis and try to understand the right projections?
So it's certainly the case that, so in CFT, you have these things called topological defects. And of course, these MPO symmetries are just lattice representations of those topological defects. So say you want to do your favorite rational CFT, you have to look at the chiral algebra of that CFT. And for each chiral, each object in your chiral algebra, you have such a topological defect. So you better make sure that the MPO symmetry algebra that you start out with is at least a subalgebra of that chiral algebra of the CFT you want to go to in the end. Now, the expectation is that generically, so if you look at the minimal models example, for example, if you look at something like the tricritical Ising model, this has an Ising subalgebra as its chiral algebra. So indeed, if you start from an Ising string net, you can map to the tricritical Ising model, but generically you expect that you will obtain the model that has the lowest central charge. Because of the C theorem, if you perturb the CFT, you will flow to something with a lower central charge, and the MPO symmetries only protect against so many relevant perturbations. If you have all the MPO symmetries associated, so if you have a lattice representation of all the topological defects of your rational CFT, you are protected against all relevant perturbations, and there is no perturbation that you can do that will change the CFT. But if you have only a subset of these MPO symmetries, well, generically you expect that you will have such a perturbation in there, and generically you expect that you will obtain the lowest CFT associated, well, that is compatible with this MPO symmetry algebra.
But is there a canonical projection? Like, so,
no, not really. So, well, this is something that we're still figuring out. So indeed, if I had to make a general claim, then I would say that the CFT that you get out generically is the CFT with the smallest central charge that has the MPO symmetries built in as topological defects. But there are cases where this is just not, you get a richer CFT out of some smaller string-net model. This is something that you have to look at on a case-by-case basis.
Okay, thanks. Are there any other questions?
I could I guess ask something, but it won't be a very good question, I imagine. So you had was the Suzuki thing with like where you were able to have like a category that extended the Z2 thing to the Z3 thing.
Yes.
Seems like you could easily extend this to Z4, Z5, Z6.
Yeah.
But then the Z5 or like the 5-state POTS no longer has a second order phase transition. So what happens there?
Yeah, that's a good question. So indeed, so the Tamari Yamagami categories are actually the ZN model. So indeed, all of those you describe. So for Z4, it's still a second order phase transition, if
I think so, yes.
but indeed for like the 5-state POTS model, I don't know what happens there. So I'm guessing, well, the claim has always been that the strange correlator gives you something that is critical or symmetry broken. It has to be one of these two. So yeah. I'm guessing that for the case of the 5-state POTS model, you will just get something that's symmetry broken.
Ooh.
But I don't know what fundamentally happens there. Why 5 you cut off? Why?
Sorry. Have you ever seen it be symmetry broken rather than critical?
So, well, the possibilities are for this strange correlator. I mean, there's many things you can try, right? We've only barely scratched the surface of what we can do with this. For example, for the Ising model, it turns out that if you fix these legs to be sigma, then this middle one, you can put whatever. And it will always be critical, save for 1 point. The expectation there was, well, maybe the cases where it is symmetry broken is something of measure 0. But to be honest, we really have no idea. And so proving whether something will be critical or symmetry broken is just as hard as proving that something is gapless. And this is just a hard problem. This doesn't give you, it's not a free way of proving that something is critical. So we really don't know. That's the answer to that.
Okay, cool, thanks.
And Laurens, could you just maybe briefly comment on what implications are there for the fundamental theorem of PEPS, like this whole the first part of the discussion? What do we learn about?
That's an important point, and I maybe went through everything a bit too quickly because I wanted to finish. But so if I go to this here, so you have these MPO intertwiners. So what we've derived here is that you can have different PEPS representation of the same string and model. Now these different PEPS locally, they look completely the same. There is no local operator that can discern between one PEPS or the other, because they are just different ground states of the same string and model. But you cannot distinguish different ground states of the same string and model locally. And so what we expect that these MPO intertwiners contribute to this fundamental theorem of PEPS is that, well, it shows at least that, well, of course, it's more complicated than in the case for MPS. But for example, in the case for MPS, if you have two MPS that represent the same state, then these two MPS have to have the same bond dimension. I mean, of course, you can always represent some MPS with some larger MPS, but that just means that there's some redundancy in that representation. There are some zeros that you can just throw away. So if two MPS are the same, then they have the same bond dimension. And then there exists such a Gates transformation, which is a square matrix. These MPO intertwiners, they are not square matrices. So they intertwine different PEPS representations of different bond dimension. So for example, for the toric code here, this PEPS representation has bond dimension 4, while this PEPS representation has bond dimension 2. Nevertheless, there exists, well, this intertwiner is then a 4 by 2, but it's not really, actually here it's just a matrix. So it's a 4 by 2 matrix that relates these two. So it at least shows that if you actually build explicit examples of these these more general gauge transformations for PEPS, that's at least more complicated than in the case for MPS.
Okay, thanks. Are there any final questions? Maybe Frank has a question or a comment. All right. Okay, so let's thank Laurens again.